welcome to ToKCast, episode 25, the Multiverse, part 2, a reading from chapter 11 of The Beginning of Infinity by David Deutsch. And we're moving slowly through understanding quantum theory, literally understanding quantum theory, applying realism to quantum theory, not denying that aspects of reality are not real, simply because we find that what the science is telling us is too astounding. As I've said in previous episodes, many things are astounding or surprising or amazing. That's no reason for rejecting them. At the time when evolution was first proposed, that seemed to be astonishing. But astonishment alone is not a reason to reject something. I'm not sure who said something to the effect, I'm sure I could Google it right now, but I won't bother. Words to the effect that I cannot refute an incredulous stare. And so when it comes to the multiverse and the very many people who reject it out of hand, even professional physicists working in the area, it seems to me that they're trying to use the argument from incredulity. So they are incredulous that this thing could possibly be correct. Now in the readings today, we're going to learn more about fungibility and the significance of that to the multiverse. We're also going to hear a description of the solution to some of these entanglement problems that we sometimes hear about, and how people try to claim that quantum theory seems to violate special relativity, the prohibition on faster than the speed of light travel, and David's going to explain how that cannot be so. There's also a little here about personal identity as well. And as always, there's simply some just amazing explanations of what's going on. So I'm just going to dive straight into it. We got up to the part where we were discussing fungibility in the context of finance and how money of certain kinds is fungible. Now we've just learnt about how money is legally fungible. And what this means is if you owe someone $1, they've lent you a dollar note, or a dollar bill, I think it's called in America, or here we have dollar coins in Australia. If you owe someone $1, they've lent you $1, you do not have to return that specific dollar to that person. Money is fungible. You can return any other dollar, or in any other form, pretty much that you like. 2 50-cent coins here will do just as well as a dollar coin here in Australia. So money is legally fungible. That's where we're coming from. Where we're going to is right here, where David writes, quote, "It so happens in some situations money is not only legally fungible, but physically too. And being so familiar, it provides a good model for thinking about fungibility. For example, if the balance in your electronic bank account is $1 and the bank adds a second dollar as a loyalty bonus and later withdraws $1 in charges, there is no meaning to whether the dollar they withdrew is the one that was there originally or the one they had added or is composed of a little of each. It is not merely that we cannot know whether it was the same dollar or have decided not to care. Because of the physics of the situation, there really is no such thing as taking the original dollar, nor such a thing as taking the one added subsequently. Dollars in bank accounts are what may be called configurational entities. They are states or configurations of objects, not what we usually think of as physical objects in their own right. Your bank balance resides in the state of a certain information storage device. In a sense, you own that state. It is illegal for anyone to alter it without your consent. But you do not own the device itself or any part of it. So in that sense, a dollar is an abstraction. Indeed, it is a piece of abstract knowledge, as I discussed in chapter 4. Knowledge, once embodied in physical form in a suitable environment, causes itself to remain so. And thus, when a physical dollar wears out and is destroyed by the mint, the abstract dollar causes the mint to transfer it into electronic form, or into a new instance in paper form. It is an abstract replicator, though, unusually for a replicator, it causes itself not to proliferate, but rather to be copied into ledgers and into backups of computer memories. So I'm skipping a bit here, because I've described this section in a previous episode. David talks about the fungibility of energy in physics. So for example, if it takes you 20 joules of energy to ride to the top of a particular hill, and then we say that you've gained 20 joules of gravitational potential energy, roughly speaking. I'm ignoring things like friction and the fact that your muscles aren't efficient and all that sort of stuff. Now, if you decide to roll your bike back down, if you're sitting on the bike and you're not pedaling and you're just rolling down the hill and you get halfway down, then halfway down, you've lost 10 of those 20 joules of gravitational potential energy. And in theory, if everything's working perfectly and there's no friction and all that sort of stuff, as we like to assume in physics, then you've gained 10 joules of kinetic energy. Now, it doesn't make sense which of the 20 joules originally that you gained as gravitational potential energy, which of those 20 were lost as gravitational potential energy and were gained as kinetic energy. And so this kind of fungibility is known as a configurational entity. And he also mentions that a configurational entity also includes particles in the quantum field. Quantum field theory is this idea that particles are excitations of something more fundamental still, the quantum field. And that would probably require a whole other series of podcasts, not mine, more than likely, to explain. So that's quantum field theory, the more fundamental, in a sense, version of quantum theory. So I will continue reading after that brief interlude. And David writes, quote, "If the two universes of our fictional multiverse are initially fungible, our transporter malfunction can make them acquire different attributes in the same way that a bank's computer can withdraw one of two fungible dollars and not the other from an account containing $2. The laws of physics could, for instance, say that when the transporter malfunctions, then in one of the universes, and not the other, there will be a small voltage surge in the transported objects. The laws, being symmetrical, could not possibly specify which universe the surge will take place in. But precisely because the universes are initially fungible, they do not have to. It is a rather counterintuitive fact that if objects are merely identical, in the sense of being exact copies, and obey deterministic laws that make no distinction between them, then they can never become different. But fungible objects, which on the face of it are even more alike, can. This is the first of those weird properties of fungibility that Leibniz never thought of, and which I consider to be at the heart of the phenomena of quantum physics." So just pause there, just as my reflection. Cast your mind back to the Mach Zehnder interferometer, and it contained that thing called the half-silvered mirror. And if a photon strikes the half-silvered mirror, it's got a 50% chance of going through, being transmitted through the mirror, and a 50% chance of bouncing off the mirror. And in terms of the multiverse, I'm getting it way ahead of what David is in this chapter, of course. But our understanding of what the physics of that situation is that the photon, being a multiversal object, contains uncountably infinite numbers of fungible instances. And so when it strikes the half-silvered mirror, literally 50% of the instances go through the mirror, are transmitted through, and 50% bounce off. And so this is the sense in which we can have perfectly deterministic laws which cause universes to act differently. Okay, back to the book. David writes, quote, "Here is another. Suppose that your account contains $100 and you have instructed your bank to transfer $1 from the account to the tax authority on a specified date in the future. So the bank's computer now contains a deterministic rule to that effect. Suppose that you have done this because the dollar already belongs to the tax authority. Say it had mistakenly sent you a tax refund and has given you a deadline to repay it. Since the dollars in the account are fungible, there is no such thing as which one belongs to the tax authority and which belong to you. So we now have a situation in which a collection of entities, though fungible, do not all have the same owner. Everyday language struggles to describe this situation. Each dollar in the account shares literally all its attributes with the others, yet it is not the case that all of them have the same owner. So could we say that in this situation they have no owner? That would be misleading, because evidently the tax authority does own one of them and you own the rest. Could one say that they all have two owners? Perhaps, but only because that is a vague term. Certainly there is no point in saying that 1 cent of each of the dollars is owned by the tax authority, because that simply runs into the problem that the cents in the account are all fungible too. But in any case, notice the problem raised by this diversity within fungibility is one of language only. It is a problem of how to describe some aspects of the situation in words. No one finds the situation itself paradoxical. The computer has been instructed to execute definite rules, and there will never be any ambiguity in what will happen as a result. Diversity within fungibility is a widespread phenomenon in the multiverse, as I shall explain. One big difference from the case of fungible money is that in the latter case, we never have to wonder about or predict what it would be like to be a dollar. That is to say, what it would be like to be fungible and then to become differentiated. Many applications of quantum theory require us to do exactly that. But first, I suggested temporarily visualizing our two universes as being next to each other in space, just as some science fiction stories refer to doppelganger universes as being in other dimensions. But now we have to abandon that image and make them coincide. Whatever that extra dimension was supposed to denote, it would make them non-fungible. It is not that they coincide in anything, such as an external space. They are not in space. An instance of space is part of each of them. That they coincide means only that they are not separate in any way. It is hard to imagine perfectly identical things coinciding. For instance, as soon as you imagine just one of them, your imagination has already violated their fungibility. But although imagination may balk, reason does not. Now our story can begin to have a non-trivial plot. For example, the voltage surge that happens in one of the two universes when the transporter malfunctions could cause some of the neurons in a passenger's brain to misfire in that universe. As a result, in that universe, the passenger spills a cup of coffee on another passenger. As a result, they have a shared experience with that which they did not have in the other universe, and this leads to romance, just as in sliding doors. The voltage surges need not be malfunctions of the transporter. They could be a regular effect of the way it works. We accept much larger, unpredictable jolts during other forms of travel, such as flying or bronco riding. Let us imagine that a tiny surge is produced in one of the universes whenever the transporter is operated in both, but that it is too small to be noticeable unless measured with a sensitive voltmeter, or unless it nudges something that happens to be on the brink of changing but would recede from the brink if not nudged. In principle, a phenomena could appear unpredictable to observers for one or more of three reasons. The first is that it is affected by some fundamentally random, indeterministic variable. I've excluded that possibility from our story because there are no such variables in real physics. The second, which is at least partly responsible for most everyday unpredictability, is that the factors affecting the phenomena, though deterministic, are either unknown or too complex to take account of. This is especially so when they involve the creation of knowledge, as I discussed in Chapter 9. The third, which had never been imagined before quantum theory, is that two or more initially fungible instances of the object become different. That is, what those transporter-induced jolts bring about, and what makes their outcome strictly unpredictable, despite being described by deterministic laws of physics. Pause there, my reflection. This is the thing that I emphasized last time as well, and I love that. That's just the powerful way that David Deutsch is able to explain in just a single sentence the misconception that so many people have about this particular point. People who think that determinism must mean predictability. And so I'll just read that sentence again because it's brilliantly parsimonious. And he writes, "That is what those transporter-induced jolts bring about, and it makes their outcomes strictly unpredictable, despite being described by deterministic laws of physics." And I'll keep going. These remarks about unpredictable phenomena could be expressed without ever referring explicitly to fungibility. And indeed, that is what multiverse researchers usually do. Nevertheless, as I have said, I believe that fungibility is essential to the explanation of quantum randomness and most other quantum phenomena. Pause there, just my reflection. There's just a side note as well. Quantum randomness. When we talk about quantum randomness, what we mean is that things seem subjectively random. And what subjectively random means is that from your perspective, it seems like what happens is random in certain situations. You flip a coin and one would say that it's 50% going to end up heads and 50% tails. From your perspective, your subjectivity, and everyone else on planet Earth from their subjectivity as well, the outcome is random. It could be heads or it could be tails. That's what subjective randomness is about. No one knows. No one could possibly predict with perfect accuracy. And indeed, the randomness that we get from coin flips or from dice rolls or roulette wheels and etc., etc. Those kind of random events. By the way, probabilistic as well, because we know what the possible outcomes are. Okay, knowledge won't go affecting the fact that if you flip a coin, it's 50-50, or you roll a dice, it's 1 in 6 for each face, if it's a fair dice, and so on. Okay, so when we know what all the possible outcomes are, we can do probability legitimately. I mention that because, of course, there are illegitimate uses of probability. For example, calculating the likelihood that civilization will survive over the next century, okay? Because we don't know the possible outcomes. Knowledge creation will affect that outcome. So subjective randomness is about this idea that we can't predict the outcomes of certain events, like rolling the dice, or even like whether or not something will go wrong with your car, that kind of thing. Now, in terms of the multiverse as a whole, however, nothing is random. There is no objective randomness. Nothing truly on the scale of the multiverse, according to the laws of physics, that is truly random. Because everything that can physically possibly happen actually does happen. And if you could possibly get outside of the multiverse, if you were an omnipotent God looking down, you would see that everything is simply unfolding as the laws of physics determined. Nothing was random. In other words, nothing violated the laws of physics. Quantum theory doesn't give us randomness in the objective sense that most people think, just a subjective sense, because you don't occupy all of the universes. If you were some sort of entity that was able to occupy all of the universes simultaneously and have a consciousness that occupied all of the universes simultaneously, then nothing would seem random to you. You would just see the unfolding of all the possible events. And so you would see, when you flipped a coin, you know that you would see both heads and tails, which would be a weird thing to experience, I suppose. We'll get into an entity like that in the next episode, I think. Anyway, so look out for that one. I keep promising that, by the way, that there's coming up, we will be talking about a test of quantum theory, which is going to be linked to consciousness. But I digress. Let's go back to the book. David writes, all three of these radically different causes of unpredictability could in principle feel exactly the same to observers. But in an explicable world, there must be a way of finding out which of them, or which combination of them, is the actual source of any apparent randomness in nature. How could one find out if that is fungibility and parallel universes that are responsible for a given phenomena? Okay, pausing there, and I'm skipping a quite substantial part of this chapter. Just to remind you, this is it's one of the longest. Yes, so this chapter has 47 pages, substantially greater than any of the other chapters. I think chapter 3, The Spark, was the second longest at 36. So it's 11 pages longer than the second longest chapter, if I've counted the pages correctly. And so I just highlight that for you because there's no substitute for reading the book. You should buy the book if you haven't. I'm skipping a lot of this chapter in order to explain around it. Now, the bit that I'm skipping here was about the prohibition on communicating between universes. So remember, David's telling a science fiction story about these doppelganger people, one of whom spills some coffee on another. Now, in a spaceship using a transporter. Now, could the universes, after they differentiate, communicate? And he explains all the reasons, all the things that could happen if they could, but they can't. And so I'm going to skip that part, and I would urge you to read that part, read the entire chapter, I suppose. But yes, I am just highlighting the fact I'm skipping significant parts of the book as I go through these chapters. Okay, so David writes, since there is no inter-universe communication in real quantum physics, we shall not allow it in our story. And so that specific route to explicability is not open. The history in which our crew members are married and the one in which they still hardly know each other cannot communicate with each other or observe each other. Nevertheless, as we shall see, there are circumstances in which histories can still affect each other in ways that do not amount to communication. And the need to explain those effects provides the main argument that our own multiverse is real. Pause there, just my reflection. So, of course, the reason why David has made a point of talking about the prohibition on inter-universe communication is because if there was inter-universe communication, then we wouldn't have to spend 47 pages. He wouldn't have to spend 47 pages and give many talks, and other philosophers and physicists like David Wallace wouldn't have to write vast books defending the thesis, because we would all be communicating with these other universes. We would see them directly, It would be easier to convince people of the existence of these other universes if it was as easy to communicate with these other universes as it was to communicate between cities or nations. But the laws of physics themselves prevent inter-universe communication. And so we have to be a bit more subtle in the observations that we interpret in order to establish that the multiverse is correct, is the way of understanding quantum theory. Back to the book. After the universes in our story begin to differ inside one starship, everything else in the world exists in pairs of identical instances. We must continue to imagine those pairs as being fungible. This is necessary because the universes are not receptacles. There is nothing to them apart from the objects that they contain. If they did have an independent reality, then each of the objects in such a pair would have a property of being in one particular universe and not the other, which would make them non-fungible. Typically, the region in which the universes are different will then grow. For instance, when the couple decide to marry, they send messages to their home planets announcing this. When the messages arrive, the two instances of each of those planets become different. Previously, only the two instances of the starship were different, but soon, even before anyone broadcasts it intentionally, some of the information will have leaked out. For instance, people in the starship are moving differently in the two universes as a result of the marriage decision. So light bounces off them differently, and some of it leaves the starship through portals, making the two universes slightly different wherever it goes. The same is true of heat radiation, infrared light, which leaves the starship through every point on the hull. Then, starting with the voltage happening in only one universe, a wave of differentiation between the universes spreads in all directions through space. Since information travelling in either universe cannot exceed the speed of light, nor can the wave of differentiation, and since, at its leading edge, it mostly travels at or near that speed, differences in the head start that some directions have over others will become an increasingly smaller proportion of the total distance travelled, and so, the further the wave travels, the more nearly spherical it becomes. So I shall call it a sphere of differentiation. Pause there, just my reflection. So this is one of the subtle and difficult, parts to really understand. So all we've got is a quantum event happening here in the starship. The transporter's been used and it causes a voltage surge in one of the universes and not the other. That's our little quantum event, a little voltage surge caused by electrons doing something or other. Now, that voltage surge magnifies up to cause, in the universe where it happened, but not in the universe where it didn't. In the universe where it happened, someone to spill their coffee. Okay, they got zapped, and so they spilled their coffee. And they spilled the coffee on someone else. And so automatically, we've magnified the quantum event to something larger. And the person upon whom the coffee fell has then talked to the person who spilt the coffee. And they've developed a romance and decided to eventually get married. Now, as soon as the coffee gets spilt, maybe the person stands up. And so automatically they're moving differently in that universe compared to the other, where they're still probably just sitting beside each other or something. And so because they're moving differently, the light's reflecting off them differently. And so to first approximation, what happens is that light that's been reflected off them is going to strike the walls of the starship in slightly different ways, and could indeed cause the heating of the starship in slightly different ways, and that heat leaks out as infrared radiation. Now, there's a lower limit on that we're going to learn about, which goes to the photoelectric effect, which we talked about in a couple of episodes back. If you recall, the photoelectric effect talks about how there is a lowest possible energy of light, namely the photon. And if you don't exceed that lowest possible energy, then perhaps nothing happens. Okay, that's a possibility that nothing happens. Over time, however, the fact that people get married in one universe but not the other causes the entire universe there to gradually change. But in what sense are the two universes kind of different? Well, they differentiate. So initially, the only difference is that in one universe, coffee is spilled and the other coffee is not spilled. The remainder of the entire universes are perfectly fungible. But over time, at approximately the speed of light, as David has said there, this wave of differentiation spreads out from the coffee spilling incident, causing all sorts of differences. But in particular, it is changed due to the knowledge. Namely, if they decide to get married in one universe, then they're going to send messages to their home planet or whatever to their families, and that's going to cause big changes. Well, big changes within the lives of those people. But the rest of the universe might only subtly change. And in fact, in some areas, barely at all. But as time goes on, those changes do affect, something the size of the classical universe. But it will take a long time for that to happen, clearly, because light only travels at 300,000 kilometers per second, and it's going to take some billions of years to get from one from one part of the universe to another very, very distant part of the universe. And so this is how differentiation happens. And it is why David Wallace called his book The Emergent Multiverse, because the multiverse is a theory not simply to explain small things that are happening. That's a great misconception. It's a theory to explain the differences between whole universes, between large-scale structures. Okay, back to the book where David's saying kind of the same thing that I just said there, but better. So I'll read that quote. Even inside the sphere of differentiation, there are comparatively few differences between the universes. The stars still shine, the planets still have the same continents, even the people who hear of the wedding and behave differently as a result retain most of the same data in their brains and other information storage devices, and they still breathe the same type of air, eat the same type of food, and so on. However, although it may seem intuitively reasonable that news of the marriage leaves most things unchanged, there is a different common sense intuition that seems to prove that it must change everything, if only slightly. Consider what happens when the news reaches a planet, say, in the form of a pulse of photons from a communication laser. Even before any human consequences, there is the physical impact of those photons, which one might expect to impart momentum to every atom exposed to the beam, which would be every atom in something like that half of the surface of the planet which is facing the beam. Those atoms would then vibrate a little differently, affecting the atoms below through interatomic forces. As each atom affected others, the effect would spread rapidly through the planet. Soon, every atom in the planet would have been affected, though most of them by unimaginably tiny amounts. Nevertheless, however small such an effect was, it would be enough to break the fungibility between each atom and its other universe counterpart. Hence, it would seem that nothing would be left fungible after the wave of differentiation had passed. These two opposite intuitions reflect the ancient dichotomy between the discrete and the continuous. The above argument that everything in the sphere of differentiation must become different depends upon the reality of extremely small physical changes, changes that would be many orders of magnitude too small to be measurable. The existence of such changes follows inexorably from the explanations of classical physics, because in classical physics, most fundamental quantities, such as energy, are continuously variable. Pause there, this is just my reflection. Okay, so just to emphasize that. So there's this thing called the inverse square law, okay, and it works for the intensity of light. And it's a classical law, and it says that as you move away from the source of light, like the sun, the intensity of light that you receive from the sun, usually measured in something like the number of watts, okay, that's the power, the number of joules of energy per second that you receive from the sun. Well, that decreases as the square of the distance. So if you are here at Earth and you're receiving a certain amount of energy from the sun, by the way, here at the Earth, it's something like, if I remember, 1,600 watts per meter squared. So if you've got 1 meter square, you get 1,600 watts approximately. I think above the atmosphere, by the way, at right angles to the sun, under perfect conditions. But if you are twice the distance away from the sun, then the square of that is 4. Okay, so you've doubled the distance. So the intensity is 4 times less than the 1,600 watts. So it would go down to 400 watts. And then if you go still further away again, so you double your distance again, then it's a quarter of that. You're now down to 100 watts. And so this is what the inverse square law is, which would say that it doesn't matter how far away you go from the sun, there will never come a point where the light disappears completely or is unable to affect you whatsoever, because it's just a continuous beam of light, right? It just gets more and more dim the further and further you get away. It never actually disappears. But we already know, don't we, that light is made of photons. So there must come a distance where you're not going to get a continuous stream of light. Eventually the light will go out. It'll disappear. And then it will start to flash at you. And the flashes will become less and less frequent. And that's what the photon theory of light is all about. Okay, so I'll just go back and read forward a little bit. So David wrote and writes, quote, "The existence of such changes follows inexorably from the explanations of classical physics, because in classical physics, most fundamental quantities, such as energy, are continuously variable. The opposing intuition comes from thinking about the world in terms of information processing, and hence in terms of discrete variables, such as the contents of people's memories. Quantum theory adjudicates this conflict in favour of the discrete. For a typical physical quantity, there is a smallest possible change that it can undergo in a given situation. For instance, there is a smallest possible amount of energy that can be transferred from radiation to any particular atom. The atom cannot absorb any less than that amount, which is called a quantum of energy. Since this was the first distinctive feature of quantum physics to be discovered, it gave its name to the field. Let us incorporate it into our fictional physics as well." Pause there, just my reflection. One might also say it was an unfortunate first discovery, this idea of the quantum, because people now think that quantum physics is really only about the very small. But of course it's not. It's about everything. It's a physical theory that explains the behaviour not only of small things, but of all things, to some extent. It's not going to explain why history happened the way that it did. It's not going to explain whether you should get married or not. It's not going to explain areas of mathematics and biology, but it is going to explain the fact that physical reality, on even the larger scales, is constituted of many different universes. And that's the biggest structure that we know of in reality, is the entire multiverse. So far from being a theory of only the very small, it also happens to be an explanation of the very largest structure that we have ever invoked in science. Okay, let's keep going. David writes, "Hence it is not the case that all the atoms on the surface of the planet are changed by the arrival of the radio message. In reality, the typical response of a large physical object to very small influences is that most of its atoms remain strictly unchanged, while, to obey the conservation laws, a few exhibit a discrete, relatively large change of 1 quantum. The discreteness of variables raises questions about motion and change. Does it mean that changes happen instantaneously? They do not, which raises the further question, what is the world like halfway through that change? Also, if a few atoms are strongly affected by some influence and the rest are unaffected, what determines which are the ones to be affected? The answer has to do with fungibility, as the reader may guess, and as I shall explain next. The effects of a wave of differentiation usually diminish rapidly with distance, simply because physical effects in general do." Pause there, my reflection. This is the inverse square law thing. So I'll skip past that. And then he writes, let me just continue here, okay? David writes, "Even the most violent of quasar jets, when viewed from a neighbouring galaxy, would be little more than an abstract painting in the sky. There is only one known phenomena which, if it ever occurred, would have effects that did not fall off with distance, and that is the creation of a certain type of knowledge, namely a beginning of infinity. Indeed, knowledge can aim itself at a target, travel vast distances, having scarcely any effect, and then utterly transform the destination. That's absolutely worth reading again, because many people who have become enamored by this book and who've talked about it in large forums have rightly fixated on that amazing observation by David Deutsch. So again, he says, knowledge can aim itself at a target, travel vast distances, having scarcely any effect, and then utterly transform the destination. End quote. So this is truly astounding, because it means that knowledge is very much a kind of physical force. Not in the strict sense of the way physicists talk about what forces are, but certainly a quality of nature, force of nature, a thing that exists in the universe, that is up there with things like gravity. If you had a God's eye view of the universe and you were trying to explain what the things are that are in that universe causing it to behave the way that it did and appear the way that it did, you would certainly cite gravity as being of key importance. Why are planets spherical? Why are so many objects in the universe spherical, approximately speaking? Stars, planets, moons. Well, because gravity pulls things into spheres. Okay? It causes things to take on spherical shapes. And the thing that stops them from collapsing, if gravity is pulling them in, are often some kind of other chemical force pushing outwards. In the case of the Earth and rocky type planets, it's the chemical forces, the electrostatic forces stop the thing from collapsing any further than it does. So you would invoke these physical forces to explain the appearance of the universe. But looking at the surface of the Earth, you can't invoke only the physical forces. Yeah, here's a picture of Sydney. This beautiful city. Now, the Sydney Harbour Basin there, it's made of sandstone. Can't see the sandstone here though. But the harbour is there because it has slowly eroded away over time through the sandstone. And that's been washed out into the ocean, the sandstone. And forms out lovely beaches, in fact. The erosion of the sandstone beneath Sydney. But the bridge, the opera house, the buildings, they're not natural formations. They're a consequence of knowledge. And indeed, knowledge being transmitted from one place to another. You know, some of this knowledge was created here, but vast amounts of it were inherited from Europe or the United States. In the future, we're going to have a moon base or a base on Mars. That will be caused by knowledge from the Earth aiming itself at that place and transforming that planet. And in the far distant future, when we look at the galaxy as a whole, one would hope that on galactic scales, when we look at certain features of the galaxy, we're going to see some areas far brighter and some areas far more dim than galaxies that are not populated by people. They will simply look different. On gross scales and at finer scales, they will look exceedingly more different. We might be able to roughly predict what planets on the other side of the galaxy look like now. They're probably going to look similar to the planets that are here in our solar system. Gas giants with pretty clouds, rocky planets that are barren like Mars or Mercury. Perhaps now and again we'll get an interesting one like Earth, which has oceans and maybe some bacteria or something like that. More or less, within certain limits, we can probably guess what the planets are going to look like. They're going to be spherical. They're going to, in general, be orbiting stars. what we can't possibly predict is what parts of the galaxy will look like if people get there. If there are places in the universe where there are people, not like us, aliens, we can't predict what they're going to be like. We can't predict what life forms will be like if they've evolved there as well. Some science fiction writers have talked about the possibility of silicon life forms. There's good reasons to think they won't happen. They won't exist. But if they did, if they were able to evolve, evolution brings knowledge into reality in such a way that it can transform it in ways that are unpredictable. But the explanatory type knowledge, it can be taken from one place, like the Earth, and perhaps in the distant future, aim itself, let's say, to a planet, orbiting a star 100 light years away, and utterly transform that planet. And in between us and that place, it might have scarcely any effect, as David says. And it will only have an effect, the desired effect, at that planet by transforming it, causing the people that are there, or the robots or whatever, to take the resources that are there and rearrange them to construct new things, new kinds of ways of creating knowledge there, civilizations and so on. So that is a really, really profound sentence, as always, buried here in the beginning of infinity, which sometimes you can just skim over without realizing the import of. Okay, let's go back to the book. David writes, quote, "In our story too, if we wanted the transporter malfunction to have a significant physical effect at astronomical distances, it would have to be via knowledge. All those torrents of photons streaming out of the starship and carrying, intentionally or unintentionally, information about a wedding will have a noticeable effect on the distant planet only if someone there cares about the possibility of such information enough to set up scientific instruments that could detect it. Now, as I have explained, our imaginary laws of physics, which say that a voltage surge happens in one universe, but not the other, cannot be deterministic unless the universes are fungible. So what happens when the transporter is used again after the universes are no longer fungible? Imagine a second starship of the same type as the first and far away. What happens if the second starship runs its transporter immediately after the first one did? One logically possible answer would be that nothing happens. In other words, the laws of physics would say that once the two universes are different, all transporters just work normally and never produce a voltage surge again. However, that would also provide a way of communicating faster than light, albeit unreliably and only once. You set up a voltmeter in the transporter room and run the transporter. If the voltage surges, you know that the other starship, however far away, has not yet run its transporter, because if it had, it would have put a permanent end to such surges everywhere. The laws governing the real multiverse do not allow information to flow in that way. If we want our fictional laws of physics to be universal from the inhabitant's point of view, the second transporter must do exactly what the first one did. It must cause a voltage surge in one universe and not in the other. But in that case, something must determine which universe the second surge will happen in. In one universe but not the other is no longer a deterministic specification. Also, a surge must not happen if the transporter is run only in the other universe. That will constitute inter-universe communication. It must depend on both instances of the transporter being run simultaneously. Even that could allow some inter-universe communication as follows. In the universe where a surge has once happened, run the transporter at a prearranged time and observe the voltmeter. If no surge happens, then the transporter in the other universe is switched off. So we are at an impasse. It is remarkable how much subtlety there can be in the apparently straightforward binary distinction between same and different, or between affected and unaffected. In the real quantum theory too, the prohibitions on inter-universe communication and faster-than-light communication are closely connected. There is a way, I think it is the only way, to meet simultaneously the requirements that our fictional laws of physics be universal and deterministic, and forbid faster-than-light and inter-universe communication. More universes. Imagine an uncountably infinite number of them, all initially fungible. The transporter causes previously fungible ones to become different, as before, but now the relevant law of physics says the voltage surges happen in half the universes in which the transporter is used. So if the two starships both run their transporters, then after the two spheres of differentiation have overlapped, there will be universes of four different kinds, those in which a surge happened only in the first starship, only in the second, in neither, and in both. In other words, in the overlap region, there are 4 different histories, each taking place in 1/4 of the universes. Pause there, my reflection. This is the full Mach-Zehnder interferometer type thing where you end up with these 4 different possibilities if you've got 2 half-silvered mirrors, because you get transmission, reflection, reflection, transmission, reflection. So you get that, and if you want to know more about that, go back a couple of episodes and have a look at the Mach-Zehnder interferometer explanation that I gave. So you end up with this one event, so to speak, causing this differentiation into 4 different kinds. Okay, I'll just, let's go back to the book. David writes, quote, "Our fictional theory has not provided enough structure in its multiverse to give meaning to half the universes, but the real quantum theory does. As I explained in Chapter 8, the method that a theory provides for giving a meaning to proportions and averages for infinite sets is called a measure. A familiar example is that classical physics assigns lengths to infinite sets of points arranged in a line. Let us suppose that our theory provides a measure for universes. Now we are allowed storylines such as the following. In the universes in which the couple married, they spend their honeymoon on a human-colonized planet that the spaceship is visiting. As they are teleporting back up, the voltage surge in half those universes causes someone's electronic notepad to play a voice message suggesting that one of the newlyweds has already been unfaithful. This sets off a chain of events that ends in divorce. So now our original collection of fungible universes contains 3 different histories. In one, comprising half the original set of universes, the couple in question are still single. In the second, comprising 1/4 of the original set, they're married. And in the third, comprising the remaining 1/4, they're divorced. Thus, the 3 histories do not occupy equal proportions of the multiverse. There are twice as many universes in which the couple never married as there are in the universes in which they are divorced. Pause there, my reflection. Mach-Zehnder interferometer again. Similar kind of number of breakup proportions, okay? It's 1/2, 1/4, 1/4. Back to the book. David writes, quote, "Now suppose that the scientists on the starship know about the multiverse and understand the physics of the transporter, though note that we have not yet given them any way of discovering those things. Then they know that, when they run the transporter, an infinite number of fungible instances of themselves, all sharing the same history, are doing so at the same time. They know that a voltage surge will occur in half the universes in that history, which means that it will split into 2 histories of equal measure. Hence, they know that if they use the voltmeter capable of detecting the surge, half of the instances of themselves are going to find that it has recorded one, and the other half are not. But they also know that it is meaningless to ask, not merely impossible to know, which event they will experience. Consequently, they can make 2 closely related predictions. One is that despite the perfect determinism of everything that is happening, nothing can reliably predict for them whether the voltmeter will detect a surge. The other prediction is simply that the voltmeter will record a surge with probability 1/2. Thus, the outcomes of such experiments are subjectively random from the perspective of any observer, even though everything that is happening is completely determined objectively. This is also the origin of quantum mechanical randomness and probability in real physics. It is due to the measure that the theory provides for the multiverse, which is in turn due to what kinds of physical processes the theory allows and forbids. Notice that when a random outcome, in this sense, is about to happen, it is a situation of diversity within fungibility. The diversity is in the variable what outcome they are going to see. The logic of the situation is the same as in cases like that of the bank account I discussed above, except that this time the fungible entities are people. They are fungible, yet half of them are going to see the surge and the other half not. In practice, they could test this prediction by doing the experiment many times. Every formula purporting to predict the sequence of outcomes will eventually fail. That tests the unpredictability. And in the overwhelming majority of universes and histories, the surge will happen approximately half the time. That tests the predicted value of the probability. Only a tiny proportion of the instances of the observers will see anything different. Pause there, my reflection. So there's a hint at the testability of the multiverse. And against classical rivals. Okay, so classical physics says the same thing can happen over and over again. This is classically what science says. The whole point of repeating your experiment to find out whether or not it's reliable is to see whether you get the same outcome each time. Well, here, if we repeat the experiment, we should find that we won't get the same result every single time. If there's a situation in which it's 50-50, then we should get different results every single time. Well, not every single time. We should approximately, we should approach the 50-50 limit. Okay, so my reflection here, I'm going to skip another substantial part here. And David talks about how the sphere of differentiation, as it spreads out, it too can cause differentiation in probabilistic ways, okay, or ways that are subjectively random. And so although the first thing that happened was this quantum event, this voltage surge and the spilling of coffee, the wave of differentiation that spreads out can then differentiate at each time a thing could have happened one way or the other, or in many different ways. All the possible outcomes happen. And so that causes, quote from the book, the number of histories continues to increase exponentially. And soon, there are so many variations on events that several significant changes have been caused somewhere in the multiversal diversity of the starship. So the total number of such histories increases exponentially too, even though they continue to constitute only a small proportion of all histories that are present. Soon after that, in an even smaller but still exponentially growing number of histories, uncanny chains of accidents and unlikely coincidences will have come to dominate events. I put those terms in quotation marks because those events, namely the accidents and the unlikely coincidences, those events are not in the least accidental. They've all happened inevitably, according to deterministic laws of physics. All of them are caused by the transporter. And David's pausing there, just my reflection. And this is where I think I'll end it today, because we'll get to this. David does write about this, or not in these words. When I was learning about the multiverse version, David introduced me to so-called Harry Potter universes. So I'll give you my take on what Harry Potter universes are like. They kind of follow this idea here. Because you can have these chains of extremely unlikely events in a very small measure of universes, but still, exponentially increasing in number, what could happen is this, okay? There could be literally a universe in which you have some teenage bespectacled boy who carries a wooden stick. And each time he does this with the wooden stick and says abracadabra, a spark comes out of the wooden stick. That's perfectly consistent with the laws of physics. Electrons can gain enough energy to come out of wooden sticks. They can just happen, right? The quantum theory says things very bizarre. Like here's a simpler example, right? I have a glass of water. Now, interesting thing about water is that at sea level, it has a boiling point of 100 degrees Celsius. So if we heat this water on a stove, then at 100 degrees Celsius it starts to bubble away, and it will all disappear if you continue to boil it. That's not surprising. So if water has a boiling point of 100 degrees Celsius, an interesting question is, why should it evaporate right now? If I leave this here for long enough, at a mere temperature in this room right now of about 23 degrees Celsius, eventually, after a long enough time, it will all evaporate away. But it's not boiling. So how does evaporation work? Because evaporation can happen at any temperature. The solution to that is that the 23 degrees Celsius water that's in here, let's say, that's the average. Temperature is a measure of the average kinetic energy, roughly speaking, of the particles of water in here, the H2O molecules. An average means that some of them have much less energy than 23 degrees Celsius, and some of them have energy much higher than 23 degrees Celsius. Some of them have a temperature, effectively, have a motion that corresponds to a temperature above boiling point. And so those ones boil away. And so as they boil away, in fact, it causes the temperature to go down, because you're losing the highest energy ones. But you can't possibly take away all the high energy ones, because although the average might go lower and lower, it's getting heat from the environment as well. So this is how evaporation in general works. Now, it is consistent with the laws of physics that because it's an average, it could just happen that all of the particles, like why does any one particle have a temperature or a motion that corresponds to a temperature above 100 degrees Celsius? Why should any one of them have that? By chance. Could more than the average have a temperature of above 100 degrees Celsius? Yes. Could all of them, according to what we know about physics, could all of them just by chance have a temperature above 100 degrees Celsius? Yes. Exceedingly unlikely. Exceedingly unlikely. I would never expect to be drinking this and suddenly to be scalded and burnt, because the proportion of universes in which that happens is so exceedingly small. But that's the principle, right? The principle is that randomly, all of the molecules in this glass of water could exceedingly rarely start moving so fast that the entire glass of water here boils. What's that got to do with Harry Potter universes? Well, the boy in some universe somewhere, the bespectacled boy with his wand, with his stick, goes abracadabra and a spark comes out. That's exceedingly unlikely, but it could happen. It could happen once. According to quantum theory, it could continue to happen. It's not the fact that the spark is caused by the boy doing this or saying abracadabra, uttering the magic words. There's no causal effect between those things. It's perfectly consistent with the laws of physics. It just happens by chance that these electrons go flying out of the end of the stick, but in his head and all people around him, they think, wow, Harry Potter has the ability to actually do magic. Perhaps he keeps on doing this throughout his entire life, and every time he does that, the spark comes out. And so he apparently is a wizard who is able to have lightning come from his wand. And so he appears to be a wizard. But he only appears to be a wizard. It only appears to be the case that magic works. Magic doesn't actually work. And in fact, if there is a universe in which, and there is, where a boy has gone abracadabra and the spark has come out, the overwhelming majority of universes then are such that the second time he does it, it would never happen again. It won't happen. Or the third time, or the 10th time, or the millionth time he does it. It's just not going to happen again. But in some universes, it will happen once. In a lesser number of universes, it happens twice. In a lesser still number of universes, it happens 3 times. You get my point. There will be some exceedingly small number of universes where every time he does it, it works. Well, I say works. It appears to work, or that event happens. The spark comes out. And so we termed these universes, such universes, Harry Potter universes, where exceedingly rare events happen. And the people in those universes could concoct a story about how magic works. And so there are places, as David will explain in the part that I'll read next time, where bizarre fiction appears to be true. Or in fact, it in certain bizarre types of fiction are true. But not... that doesn't mean that that things are causal there. So this has to do with whether or not the knowledge they have there is valid. And this goes deep into the idea of information flow. So there we've got a whole bunch of chance coincidences. Okay, the saying of the abracadabra, the spark flying out of the stick, and therefore people referring to the stick as a wand and to the spark as magic, and Harry Potter in that universe as a wizard. Even though the stick is just a stick. The spark is just a spark. It's not magical lightning. Harry Potter is just a kid with spectacles. He's not a wizard. But people in those universes, they don't know because it's just been freak coincidences. But that's an exceedingly small number of universes. One would expect a number of universes smaller than the number of universes in which suddenly all of the water in all of the oceans on planet Earth has boiled away instantly. It's happened somewhere in the multiverse, but the measure of universes where that's happened is so tiny as to not really be of anything other than purely academic interest. Okay, so more on that next time. I hope this one was enjoyable. Until next time, see you. Bye.